Okay, yeah, we're all set. So, yep, things settle. Okay, so my talk will be about the networking aspects of data availability sampling, specific to the Ethereum context. This is a work that we jointly done by Leonardo and Dimitri, who are my colleagues at Status. Status you might know from the Status Hub, from Keycard, from the Nimbus client. And we are all in the Codex team, which is working on decentralized storage technologies. And this work is funded by an Ethereum Foundation grant. So thanks to the Ethereum Foundation, we can work on this. So what is data availability sampling and why we need it? As I said, we are focusing on the Ethereum context. So data availability sampling is a generic technique, but in the Ethereum context, it's really the new key to scale Ethereum. So the goal, what we have here is really increase the block size beyond what a single node can handle without really making the nodes heavy, so without changing the requirements on the nodes themselves. So the question we should pose ourselves is how can we go and increase the block size so that put ourselves in a situation where nodes cannot download the block and yet have the system working. And thinking of this, there was sharding, proto-dank sharding, dank sharding. There are some underlying realizations. I was listing here 3. One is that there is data, which is sitting in data blobs, which nodes do not have to interpret. So if nodes do not have to interpret it, they actually don't need to download it to interpret it. They're really downloading it for something else. Currently, they are downloading it. And what they are downloading for is really to know that the data is available, that the data was released, that it's not withheld. So that's the only reason they are downloading. So you can do something else. And the something else that you can do is sampling. It's probabilistic sampling. So the other realization is you don't have to go deterministic and download all the block. You can do a probabilistic sampling, a statistical test. And based on that, you can hope to be lucky enough to figure out if data was not actually released, and thus you know that the data is not available, and you can disregard that block. So we arrive to sampling, and as I said, we have a statistical test. The data, the block is segmented, and there's a sampling process going on, picking a piece, or maybe more pieces of the many pieces, and based on that, deciding whether we believe the data is available or we don't believe the data is available. So the first thing we do is segment and sample. So the data is in some state. It's either available or not. And it's segmented, and you're asking for one of these pieces. And if there were k segments and you are asking for one of these k segments, you have 1/k probability that you figure out that it was not available if you're on the right side. If you're on the left side and it's available, you're fine. You will always find it available. And you can ask for more samples. You can ask for S samples of the many k pieces, and you have this linearly growing probability of figuring out that it's not available if it's not available. The problem is that this is linearly growing, so you're not really gaining anything with the sampling. Statistically, this is quite wrong. So what you do is you are extending the code. You are using read-sum encoding, erasure coding, and you are extending the data. You are adding read-sum encoding, which has the base property that if any k, in this example 4, of the pieces are available, of the extended 8 pieces, then you can reconstruct the data. So when it's all available, it's fine. But what you see below is also repairable. Right? So you have 4 pieces missing, the red ones. 4 pieces are there, 2 which were generated parity data, 2 of the original pieces. So you can reconstruct the data. So you can look at it as the data being still available. This interesting part is when 5 pieces are missing, and then the data is not available. And in that case, you have kind of 1/2, in this example a bit more probability, but if there are many segments, it's 1/2 probability that you figure out that the data is not there with one little single sample. And the nice thing is that if you have 2 samples, you have 0 or 4, and if you have S samples, you have 1 minus 1 minus 1 over 2 to the k probability of figuring out. So it's kind of vanishing probability with the number of samples, if you have many segments, that you figure out with a statistical test that the data is not available. And we are happy with this. No, we are not. Because there is a problem. There was a read summon encoding, we think, but actually we don't know that those pieces which were there can be used to regenerate the original data. They can be just random data. We will sample it. We will find out that the piece is there, a piece is there, something is there, and we believe that the data is there because our test is showing that. But they cannot actually be used to reconstruct the data. So in the example you see there, actually there are 5 pieces missing. We just don't know. We sample, we get something, we believe it, and that's wrong. So that's why we have to segment, we have to extend the data, then we have to prove each single piece, and then we will sample. So what's happening is that we are proving the read summon code, and this is going with a KZG commitment. So there is a commitment to the data. Each single sample proof has, each single segment has a proof attached. So if you have the commitment, a single segment, and the proof, these together enable you to verify that the sample is actually coming from the correct read summon encoding. So your math is working again. If you sample and you get something, you know it can be used to reconstruct. So once you segment, extend, prove, and sample, you are having something which can be used to guess whether the data is available or not. Now, this would be very nice, but this is not what is being planned in Ethereum. That's a slightly bit more convoluted. It's just a nice little step. So this is what it is. So this is how block encoding is planned in the next evolution. Where the K that you see there, the 64K is not the K that you've seen before. This is kilo. So this is 64,000 segments. So the data block, which is 32 megabytes, is divided into 64,000 segments, which is half a kilobyte per segment. And then over this, there is a read summon encoding, but it's not a normal read summon encoding. It's a 2-dimensional read summon encoding, which has a nice property that if you have K pieces, so it's in this case 256 pieces of an individual row, then you can reconstruct the row. Or if you have 256 pieces of an individual column, then you can reconstruct the column. So it is extended to 256,000 segments, each one being half a kilobyte, and we have 128 megabytes of data. And this is kind of our new block that we are going to sample on. And of course, there are KZG commitments. So you see the numbers there. For the 128 megabytes of data, you have something like, I don't find it now. 12 megabytes of KZG commitments added. So you have this extended set of data, of which the top left corner is the original data. And sampling is going over this. Now, let's have a little quiz. So is data available if these segments are there, the blue ones, and the white segments are not there? And you would say, yes, this is the original data. This is data from which the extra data was generated. So obviously, this is repairable, and this is available. And with rows and columns, you can easily repair it. You can see, I repair the row. You can repair all the rows. From those, you can repair all the columns. And yes, it's repairable. Let's take another example. Is this repairable or not? And this doesn't seem that obvious, right? But if you see that you can repair that column, for example, you see that you can repair all those, that row, you see that you can repair all those rows, and you can repair the columns, and at the end, yes, that was repairable. What about this one? Maybe notice that in these, going back a little bit, only 25% of the data was available. So what about this one, where we have almost 75% of the extended block available? Sounds like repairable, right? But actually it is not. It is not because you cannot repair anything. There is no row or column where you can start repairing. In every row or column, you either have a row or column already there, so you cannot repair it because it's already repaired, or you have only 3 pieces, so you cannot start repairing. So this is a no, right? What about this one? So there are different reasonings here. One is we just simply don't have enough data to have it repairable. It's less data than the original data. It can't be repairable. You can extend it, and you get back to the previous one, and you see this is not repairable. So we have this nice data structure, and we understand how repairing works on this, and we understand how sampling into this could work. But actually, this is not done locally. This is done over the network. So let's see the networking perspective. Let's see what happens on the network, actually, when we are sampling. So how we check data availability over the network in the context of Ethereum. So notice that in the context of Ethereum, there are different nodes, and they have different goals. So validators and full nodes have different goals that they want to achieve from this extended set of data. Validators, the goal is they should either generate many attestations if the data was available, or they should generate very few attestations if the data was not available. And that's the system level goal. We don't like things in between. For nodes, it's a bit different. They want to find out, with a very high probability, during the statistical sampling, if the data is not available. Because if it's not available, then it can be a block, which maybe it was even validated, but maybe there is some supermajority malicious among the validators, or maybe for other reasons. It should not be accepted. So if it figures out that it is not available, then there might be data withhold, and depending on the use of this data, whether it's used for an optimistic rollup or whether it's used for a ZK rollup, there are different use cases, but for each one of these, if the data is withhold, it can be a huge problem. So we have to get the data from the block builder to the validators and to the nodes in a way that they can satisfy this. So it's actually a process which goes through many steps. There are individual places here. So there is the block is being created, extended, as I was showing. Then the block proposer or the builder is disseminating the rows and the columns to the validators, and the validators do the job of validating or not. And then there is another thing, which is the data is pushed into a neutral structure, a DHT, from which then the nodes can sample. And then this structure might also need repairing because nodes are leaving, there is churn. So there are all these processes going on behind the scene. Now today I will focus on the dissemination of samples to the validators. So I will not go into the DHT part, and I will not go into the actual sampling over the DHT. But let's see what happens between the block producer and the validators. So from builders to validators. Each validator is checking a number of rows and columns, and by default we are speaking of 2 because it's an easy example. It's a variable parameter at the moment. So each validator is selecting randomly 2 rows and 2 columns, and they are checking that. And that's the check. Is it there or not there? And just to give you a bit of dimensions of the problem, so we have 500,000 plus validators, around 8,000 plus beacon nodes, behind which these validators are sitting. You have those 260K segments, which are sitting in 1,024 rows and columns. And we have something like 4 seconds to do this. So how do we do it? There are different proposals out there. The base proposal that I'm speaking of now is to use a gossip sub, or a gossip sub-like protocol, I would say, because I don't think it will be the gossip sub as of now, whichever version. So we use a gossip sub-like protocol, and we knew a number of topics in gossip sub. So if you know gossip sub, you know what it means. If you don't know, gossip sub is building a mesh network, like you see there. Those are beacon nodes behind which you have validators which are interested in the 243rd column, and they form a small mesh network with a given degree in which they are sending the column so that everyone has it. And you have 1,024 of these networks built. And we like gossip sub, and we like gossip sub-like protocols because they are robust. They have different reliability mechanisms. So one is that they are building this mesh to push. They are sending gossip messages so that nodes can pull information. And they have also, using reliable transport, they are using TCP. Gossip sub also has downsides. They send lots of duplicates, and they are not yet ready for large messages. But you've seen we are not just using the gossip sub here. We have 2 more technologies here. Like you have the erasure coding, and we have this 2D structure. So we are adding 2 more layers of reliability. We have the Reed-Solomon code, which we can use as a forward error correction code from communications, if you know that. So basically, if you have half the row, if you received it, your node, you received half, whichever half number of segments, you can repair it. And the topics are cross-connected. So if you receive something on a row, you have it on a column. So we can use these 2 techniques as well. So we have 5 reliability mechanisms there with which we can play to have a system which works well. So what we did is a simulator for this. It's in Python, which is nicely accessible, we hope, for others. It's very much work in progress, and everything I show here is preliminary. So don't take the exact numbers. And we do many simplifying assumptions from the networking perspective. We don't care about TCP slow start. We have 100 millisecond round trip time at the moment. And this is what you see on the right side is one single dissemination with a builder which has 1,000 megabits per second link. This is a conservative estimate, but we are not counting with some factors. We have 5,400 nodes, which are kind of solo stakers, 1 validator with a smaller bandwidth, and we have 1,600 nodes, which are having their beacon nodes handling a bunch of validators and having a better network connectivity. And what you see on the right side is kind of the progress, the evolution. So on the top, below there's the time, so we are arriving to 1 second. And in 1 second, nodes are receiving samples, and validators start to validate. Validators validate when they have all the rows and columns. And then you also see a bunch of network statistics. What is the transmission bandwidth, the reception bandwidth, and how many duplicates you have. Now how we use this. Let's see one example. This is about message size. So I said we are sending rows and columns, but you can do it in many ways. So on the left side, what you have is sending, using gossip sub with messages being rows and messages being columns. So message is 280 kilobytes. This is the big message case. And what you see there is that to validate, so that for the green curve to go up, we need something like 1.6, 1.7 seconds. On the right side, we are using small segments. So small messages. So every segment of those 260,000 is a message. And then we are much faster. Another example of the simulator is checking boundary conditions. So what you see on the top is something which we know is repairable and available. What you see at the bottom is something which we know is not repairable and thus should be not available, should not be validated. what you see on the right side is validators, basically all of them, validating what's on the left, what's on the top in a second and something. Below, what you see is that validation progress is stuck at a low percentage. Obviously, no one has more than 75% of the chunks of the segments, and this is what we wanted to achieve. So we have the simulator now. As I said, it's quite work in progress. We are using it to kind of figure out the right combinations, figure out what gossips are like means. So we are experimenting with different variations. We will improve the simulation fidelity. We will do parameter space exploration. The curves I've shown you were single runs, so they are defined and statistically relevant. Exploring attacks, and then dealing with the other parts of the dissemination to the DHT and of the sampling. So, thank you. If there are any questions.
Very good. Thank you, Csaba. Super interesting. Again, very in-depth. Any in-depth questions from the audience? Over here.
So I wonder if all the blocks that are meant to be available for the period that is under consensus are constantly sampled by the validators.
Why they are constantly sampled?
No, I'm asking is like if block availability should be like, I don't know, 2 weeks, then all the 2 weeks worth of blocks are constantly, each of them are sampled from the DHT by nodes.
Why nodes are constantly sampling it? So the validators are doing the verification because they don't validate if they don't see it available. The nodes are doing it because they also want to be protected against the case when the validators themselves have a supermajority of malicious misbehaving nodes. So it's kind of a case where they just don't believe everything to the validators.
Okay. Another question from the audience? No. Going once. Going twice. 2.5, 2.75, 2.8. Okay. Very good. Thanks again, Csaba.
Thank you.
We have just